So we have seen so far that any permutation in Sn can be written as a disjoint product of cycles, and that is very useful in particular, for example, when you want to calculate the order of the permutation, because order of the permutation will simply be LCM of the orders provided the cycles are disjoint. Next we are going to look at another decomposition for permutations which is not disjoint but it is useful in some other situations. So let us define a transposition. A 2 cycle is called a transposition. So 2 cycles are particularly simple permutations, right? What is a 2 cycle? It is something like Ij, right? So Ij is a 2 cycle. What does it do as a permutation? It sends I to j and j to I and fixes everything else. Right? So permutations which are 2 cycles are easy. They just change I to j, j to I, fix everything else. They are called transpositions because they are just transposing I and j. So we are putting I in place of j, j in place of I. We transpose them and we don't disturb their other indices. So transpositions are easy to understand, and a transposition has order 2. A transposition has order 2 because it's a 2 cycle. So 2 cycles have order 2. In general, k cycles have order k. Now let us see if we can write any element Let me write the proposition, then we will look at some examples and then prove that. Every permutation can be written as a product of transpositions or 2 cycles. But most important thing to remember is not necessarily disjoint transpositions. So we can write it as a product of transpositions, but in order to achieve this we have to give up disjointness. We cannot write disjoint as disjoint transpositions. So before proving this, which is actually not difficult at all, let us look at some examples. So let's take sigma to be 1, 3, 2 in S5. So actually it can be S3, S4, S5, S6 and so on. What does it do? It sends 1 to 3, 3 to 2, 2 to 1. So it's a 3 cycle. So remember that it cannot be written as a disjoint. We certainly know sigma cannot be written as a disjoint. So let me write it like this. Cannot be written as a product of disjoint transpositions. Why? Why can't it be written as a product of disjoint transpositions? Suppose it can be written. So if sigma is tau 1, let's say sigma 1, sigma 2, sigma k, where sigma 1 to sigma k are disjoint transpositions. So the reason for why we can't write sigma as a product of disjoint transpositions. If you can, then order of sigma is equal to LCM of order of sigma 1 because it's a product of disjoint cycles, order of sigma will be LCM of order of sigma 1, order of sigma 2, order of sigma k. But order of sigma 1 is 2, order of sigma 2 is 2, order of sigma k is 2, because they are all transpositions. So order of sigma would be 2, because LCM of 2, 2, 2, 2, any number of times is 2. But sigma is a 3 cycle. So order of sigma is, by another proposition that we have proved in some time ago, order of sigma is 3 because it's a 3 cycle. So order of, if it can be written as a product of disjoint 2 cycles, its order would be 2, whereas its order is 3. So it can't be written as a product of disjoint transpositions. However, we can write it as a product of transpositions if we don't insist on disjointness. How do we do this? So 1, 3, 2, for example, is easy to check, is 1, 3, 1, 1, 2, 1, 3. Why is this? Because you can check quickly. This sends 1 to 3, 3 to 2, and 2 to 1. What does this do? 1 to 3 under the first one, but then 3 to 3 under the second one, which is good. Where does 2 go? 2 goes to 2 under the first one, and 2 goes to 1 under the second one, which is also good. Finally 3 goes to 1 and 1 goes to 2. So these are equal, right? So 1, 3, 2 is written as a product of 2 transpositions. But they are not disjoint, because 1 is common to both. So they are not disjoint. As we know, you can't write it as a product of disjoint transpositions. I didn't mention this earlier because we don't need it, but when you write a permutation as a product of disjoint cycles, that product or decomposition is unique. It is not at all difficult to show that, because they are disjoint cycles. You can't have another product decomposition into disjoint cycles. However, because we cannot have disjoint product of transpositions, this product into transpositions is not unique. Okay, so 1, 3, 2 also happens to be 1, 3, 3, 2. Okay, as you can quickly check, what happens to 1 in this? 1 goes to 1 under the first one, 1 goes to 3 under the second one, 2 goes to 3 under the first one, 3 goes to 1 under the second one, 3 goes to 2 under the first one, 2 goes to 2 under the second one. So this is same as 1, 3, 2, right? We have proved this. So this is a different decomposition of the same element of the same permutation, namely 1, 3, 2, as a product of transpositions. Okay, so certainly it's different because it's 1, 2 and 1, 3 come here, 1, 3 and 3, 2. So there are different permutation transpositions appearing in this. So these are different decompositions. But again, it's not disjoint, right? 3 is common to both. So you might wonder, maybe the decomposition is not unique, but the number of transpositions is unique. Here there are two transpositions. Here also there are 2 transpositions. But as another example will show, even that number is not unique. So let's say I take sigma to be 1, 2, 1, 3, 1, 4. So this is a product of 3 transpositions. But you can quickly check that this is same as, I have checked this. You can do this as an exercise. 2, 1, 2, 4, 5, 1, 5. Okay. So for example, just let us randomly pick some element here. What happens to, let's say 1 under both of these. 1 under the first decomposition goes to 4, then 4 goes to 4, then 4 goes to 4. So 1 goes to 4 under the first one. What happens to 1 under the second one? 1 goes to 5, 5 goes to 4, and then 4 is not appearing there. So this is 1 goes to 4 under same. So similarly, you can check that these two decompositions are same. So here you need 5 transpositions. So not only is the decomposition into product of transpositions is not unique, even the number of them that you require is not unique. So here we need 3 and here you need 5. However, there is some uniqueness about this decomposition into a product of transpositions that I will come to later. Now let's come back to the proof of the proposition. What do we have to show? We have to show that given any permutation in Sn, it can be written as a product of transpositions. First, observe that it suffices to show that a cycle sigma can be written as a product of transpositions. Why is this? So suppose I show that a cycle can be written as a product of transpositions. Then why am I able to say that any permutation can be written as a product of transpositions? Because given any permutation, sigma, we can write sigma as sigma 1, sigma 2, sigma k, where sigma 1 through sigma k are what? Disjoint cycles. Here disjointness is not that important, but we can write it as a product of cycles. That we already know, we have proved this. Any permutation in Sn can be written as a product of cycles. Now suppose I prove that cycles can be written as product of transpositions. So sigma 1 can be written as a product of, so we have sigma 2, sigma k, but sigma 1 can be written as a product of transpositions. Sigma 2 can be written as a product of transpositions. So this is sigma 1, this is sigma 2, and so on. Sigma k can be written as a product of transpositions. Then we have written sigma, right? Remember, we are not claiming anything about disjointness. In fact, we cannot claim. There can't be a decomposition into a product of disjoint transpositions. So we don't care if repeated things happen. Sigma 1 can be written as a product of transpositions, so can sigma 2, and so can sigma k. So sigma can also be written as a product of transpositions. So we assume now sigma is a, let's say, k cycle. So we only need to consider the case of k cycles. So say sigma is I1, I2, Ik. So now if you just stare at this for a bit, you can see how to write this as a product of product of transpositions. So we can write sigma as, so I'm going to write it like this. So keep in mind that what sigma does is it sends I1 to I2. So let me put I1, I2 here. I'm going to write from left to right, but when we actually multiply, remember, to figure out the image of an index, we go from right to left. So if this is the last one that is there, and if I make sure that I1 does not appear in the remaining ones, then I1 will go to I2 under the product. So I'll do I2, I3. So now whatever I write here, let's ensure that I2 does not go to I2 does not appear in any of these. Then in order to figure out what is the image of I2 under this product, we have to keep going from right and we hit I2 here. So I2 will go to I3 under this, but then I3 is not present in this, so I2 will go to I3, which is how it should be. Now I'll put I3, I4. And I'll keep doing this. I'll do ik minus 3, ik minus 2, ik minus 2, ik minus 1, ik minus 1, ik. Okay, so I claim this. We can write like this. In fact, we claim that this is an equality. So let's check this. As I said, it's very easy to see this, but let's check one by one. Where does I1 go? And for the right hand side product, for the product on the right hand side, I1, remember, to figure out where I1 goes, we have to go from right and keep applying I1 every time we see. So I1 is not present here, so we don't, it fixes I1, so we don't care. I1 is not present here, I1 is not present in the third one from the right. It is not present in any of the first k minus 1 things. It is present only in first k minus 2 things. It is present only in the last one. So we must send I1 to I2, right? Sigma also sends I1 to I2, remember. Now where does I2 go? We have to go from right and see where I2 first appears. And the first time I2 appears, remember, the way we are writing this, I2 will not appear until we hit I2, I3. So I2 will go to I3, right? Is that clear? Because I2 is not present. I2 is already written here in I2, I3. So subsequent transpositions will only involve higher indices. So I2 will not appear there. I2 will go to I3 here. Now possibly we have to go left and see. But I3 does not appear in the previous one. So I2 will go to I3 under the product. What happens to I3? I3 will not appear until we hit I3, I4. And here it will go to I4. But then I4 no longer appears again. I4 doesn't appear here. I4 doesn't appear here. So I3 goes to I4 and so on. What happens to ik minus 2? Ik minus 2 goes to ik minus 1. The first one on the right doesn't involve ik minus 2. The second one does. So ik minus 1, ik minus 2 goes to ik minus 1. But then ik minus 1 doesn't appear again anywhere else. So ik minus 2 goes to ik minus 1. The point of this decomposition is each index appears exactly twice except I1 and ik. I2 appears here twice, I3 appears twice, ik minus 2 appears twice, ik minus 1 appears twice. But once ik minus 2 appears here, only time ik minus 1 appears next time is in the right hand side permutation. So it doesn't matter what happens previously, ik minus 2 goes to ik minus 1. Ik minus 1 goes to, so the first one itself involves ik minus 1. So we have to check ik. But then ik never appears again anywhere. So ik minus 1 goes to ik. So finally check ik. So ik goes to ik minus 1 on the first thing. Now ik minus 1 appears again. So and it sends ik minus 1 to ik minus 2. Ik minus 2 goes to ik minus 3 here. And you have to keep tracing back. Ik minus 2 goes to ik minus 3 goes to ik minus 4. I4 goes to I3, I3 goes to I2, I2 goes to I1. So in order to determine the image of ik, we start with the right hand side rightmost permutation and keep tracing it back all the way to I1. So ik goes to I1. But this is exactly equal to I1. Sorry, sigma 1. Sigma. This is exactly equal to sigma. So we have shown that sigma is I1, I2, I2, I3, I3, I4, ik minus 3, ik minus 2, ik minus 2, ik minus 1, ik minus 1, ik. And this is a product of transpositions. So we have shown that give me any k cycle I1, I2, ik I can write it as a product of transpositions. And we have already said that any permutation is a product of cycles, and every cycle can be written as a product of transpositions. So any permutation can be written as a product of transpositions. This proves the proposition. And we have already looked at some examples. So the important points to keep in mind is, first, you can write any permutation as a product of transpositions. This product is not disjoint and not unique. Even the number of transpositions required is not unique. And in the next video, I'm going to look at what kind of uniqueness we can get out of this decomposition into product of transpositions. Thank you.